All right, so thank you, Amanda. I always feel a little awkward when she says that because we've worked together for 15, 16 years. And if you really want to know who runs both the Coast Fork and the McKenzie, just kind of take a guess. So really happy to be here this evening. Thank you very much. So I'm here. I'm going to talk about a very large and exciting project that we've been implementing with the McKenzie River Ranger District, the Forest Service on the South Fork McKenzie downstream of Cougar Dam. I've got a ton of slides and I've got about 45 minutes to squeeze them all in there. And so parts of this I'm going to go really fast. And other parts I'll try to, that I think are more interesting, I'll try to actually spread out a little bit. So, and I'll try to keep the microphone close to my mouth. So, all right, so this is what we're going to do this evening. So what I'd like to do is give you a little bit of background and try to define what this kind of loaded term stage 0 actually means this evening. Talk a little bit about why we're actually working on the South Fork. And then talk about what we've done over the course of 2 years of implementation, phase 1 and phase 2. We hope to have a phase 3 and phase 4 over the next 3 or 4 years. And then talk about a really exciting monitoring project that we're actually starting actually in 2019, and then hopefully have some time for some questions. All right, so the washed out screens are not going to do us any favors this evening. But what the top of this screen says here is this term stage 0 actually comes from an academic paper by Kluwer and Thorne published in 2013. And the really interesting thing with this is that this suite of projects has been developed over the course of 10, 15 years, or at least its design and its methodology. And it wasn't really until like 2016, 2017 that the folks doing this work even became aware of the academic work and actually found this paper and then said, hey, this paper is kind of defining what we're doing. And so, oh, go back one. And so what we've come up with in terms of a definition of what stage 0 actually means is this right here. And so what we're trying to do is work on a valley scale, implement essentially from hill slope to hill slope, increase connectivity not only at high flows but at summertime base flows, and set it up in such a way that the natural processes of the river can take care and sustain their the project over time, which is a little bit different than what some of the historic restoration projects have really been focused on. I'll get to that in just a second. So I'm going to skip most of these because we can't really see them, but essentially what stage 0 is refers to, as was kind of seen in the trivia portion, is so stage 0 refers to stream evolution model, which if you've taken science classes in the last 30 or 40 years, you're probably familiar with this diagram that you can't really see here. But essentially, the stream evolution model is an idea of how streams evolve over time. And the traditional approach has been the initiating undisturbed stage is this single sinuous thread through low elevation or low gradient depositional areas. Well, this paper by Kluwer and Thorne in 2013, go ahead, proposed a different paradigm for an undisturbed, or a different idea for an undisturbed stage. And rather than go back and renumber this stream evolution number, put in a precursor stage, stage 0, that they describe as more of a braided channel network with a bunch of wetland complexes and smaller braided channels through forested systems. And the idea was that what the traditional stream evolution model was looking at in terms of undisturbed stage had been historically disturbed through eons, both artificially or natural occurrences. And so really kind of set the whole stage for, pardon the pun, for essentially a new way to look at actually how streams can be restored back to an undisturbed state. Go ahead. Really difficult slide to read here, but the other thing that this paper did was look at a couple of different models for both biological productivity and habitat diversity at all these different stages, and showed that way more productive at what would make sense is these way more diverse systems. Go ahead. Really hard to see. All right. So this is a diagram of this stage 0. Sorry, I keep hearing voices. Undisturbed state here. And so what you're looking at here is a floodplain that's connected essentially from valley to valley with braided systems, a diversity of vegetation, beaver habitat, lots of down wood. Go ahead. And go ahead again. And a stream system that has low stream power where the water table is high, and you have connectivity across the entire low gradient system. Go ahead. So how this system has really changed over time when you start implementing or installing roadways, berms, converting floodplains to other uses, whether habitat or housing, agricultural uses, whatever. You've cut off the stream from that floodplain and confined it into a single channel. And go ahead. And what you've done to that stream flow is take what was spread out across that entire wide floodplain, concentrate that into a single channel, and just think about playing with a hose back when you were a kid. And so put your thumb on that, disperses out, as opposed to one single fire hose concentrated in a single channel. That power, that velocity is way higher. And so anything in terms of habitat like complex wood, gravels, fine sediment for lamprey and little macroinvertebrates, it's easily flushed out of that system. And so when folks started paying attention to, hey, we're really changing the dynamics of our rivers back in the 70s and 80s, what can we do to restore them? One thing that came out is we can start putting large wood back in there, we can put boulders back in, but the concentration was back in that single thread channel. And so what you do, can't really see it very well, so we put in all this large wood, all these boulders into that channel, and what we haven't really thought about is how that channel is actually connected across that entire floodplain. And so invariably what happens with a lot of those systems or a lot of that historic restoration is that gets flushed out of the system because we haven't addressed that stream power concept of what was a dispersed flow and a dispersed velocity across the entire floodplain is now concentrated into a single channel. Go ahead. And so what this restoration approach tries to do is address that stream power concept by removing that those confinement elements, whether they're old roadways or levees, taking that material and actually filling those incised channels, and I'll show you those pictures here in a minute, and pushing that wood across the entire surface. So this talks a little bit about this shows a little bit some of those earlier approaches. We did some crazy things in terms of actually putting gabions in and chicken wiring or using welded wire to hold rocks in the system, cabling large wood pieces into systems, all these crazy artificial means to get roughness, to get wood, to get rocks, to actually stay in these hosed out systems. Go ahead. So that progressed a little bit. How can we think a little bit more holistically? Started using different approaches that were very heavily engineered and reliant upon these really complex designs to get a little bit more structure into the system, to get that structure to actually stay in the creek and maybe get a bit of connection to floodplains. But once again, heavily engineered, didn't really have a whole lot of natural function to it. And expensive, I'll say. Go ahead. And so the next kind of progression of this was using larger and larger wood, adding whole trees, actually tipping streamside trees into these channels to try to get a little bit of more connection with the floodplain. Go ahead. Go ahead again. This is a shame. Okay. Can't really see this very well, but there's really an interesting story with how this design approach developed. So like I think a lot of breakthroughs kind of happened by accident. So there was this Forest Service project out near Siuslaw, or not, out on the Siuslaw, out near Florence, Karnowski Creek. Very traditional system there, if you're at all familiar with Coast Range systems, small tributaries. These small tributaries that had braiding, meandering creeks through this relatively small valley. When those were settled, the creek was taken from its valley bottom, put over to the one side and channelized, and then create a essentially grazing habitat or homesteads or whatever. And so early attempts at restoring that would design and cut a very engineered, meandering channel through these floodplains. And so this is what this picture is trying to show here. Go ahead and go to the next one. Well, in this particular case, you had a landslide that came in and completely filled that channel. And the project manager was like, oh my gosh, we had a complete disaster. What are we going to have to do? We're going to have to go back in there and dig this channel back out. Brought a couple other colleagues in. They started looking at it, started talking about it, and noticed that they were getting all these really awesome floodplain features, and the fish were actually using it. So you brought that water, at this spot, you actually brought that water table back up. There were fine sediments and spawning gravels throughout this whole landslide area. And it's like, wait a second, we might have actually stumbled onto something here. Go ahead. And so this is really a shame that we can't actually see this, and maybe we can get this up on the website or something. But so they started implementing smaller scale projects across like 8-10 acres in meadows in central Oregon, where historic land use practices with grazing, vegetation removal have really incised these creeks, where they're dropped down 3, 4, 5, 6, 7 feet from what were historic wetted meadows. And they've tried a number of different restoration approaches through the years to try to bring that water table back up and change that vegetation community with some of those gabions or sill logs across the creek. Try to trap natural occurring sediment, but essentially using this stage 0 approach, where you come in and actively fill that channel, which is what you kind of see in that lower left corner, and bring that water table up in the series of a couple of weeks. What they found is within a year, they've completely brought that water table back up and changed that native plant community, which you can kind of see with that green carpet in the lower right. Go ahead. So the one that was referred to, the kind of the earliest, or the beginning of this kind of the stage 0 concept, without it actually having that name, occurred on Whitejuice Creek, which actually flows through Sisters on the Deschutes, just over the mountains here. And the idea was try to bring this with very much an incised channel, which you see in the upper right, back up to an elevation that would connect it to relic and historic side channels throughout this wide and unconstrained floodplain. And essentially what they did here was use surveyors and transits to go out and identify elevations in these what they assumed were undisturbed relic side channels and shoot those elevations across into this incised channel, White Shoes Creek, remove any barriers or levees between those two surfaces, fill in the incised channel of White Shoes Creek, and so you've taken this single thread channel that you see in the upper right into this braided network down there on the left. Go ahead. The first one that we did in the McKenzie was in 2016 on Deer Creek. If you're at all familiar with that, it's up just past Belknap. It's just off the highway. There's kind of a really small, not so hot springs that's open and available to folks. But what we did with this project, once again, without the benefit of really any tools or understanding, what we were doing with this actual term stage 0 concept was add a bunch of wood, but once again, go in there and identify those streamside berms that have been placed for a couple different reasons. If you're at all familiar with this creek, there's a E-web power lines essentially go right through the creek for whatever reason. Back in the 60s, it was the straightest and easiest way to bring power from Trail Bridge down into the Lower McKenzie, put them right through the creek, put some berms in there to confine that creek to one channel. And so this project identified those berms, take those things down, fill into this channel, and you can't really see it with this picture, but essentially you've taken that, once again, taken that single thread channel and spread it across the floodplain. Go ahead. I'm going to skip this. It's really hard to see with this washed out photo, but once again, really, so the whole point with this is that there was like almost 10 years of project development without actually having a term for it or actually having a methodology to really share and interact with other practitioners. And so it's a really good example of kind of how restoration is really kind of an evolving science and really kind of gets field fit a lot of times. And it was really with that Deer Creek project and White Shoes in particular where this methodology came together. And then there was an actual paper, go ahead. A methods paper published on actually how to utilize LiDAR to develop these projects and come up with an actual design. Go ahead. And to date, there's been about 20 projects implemented in the state of Oregon. Most are really those small scale kind of valley or meadow projects on the east side. There's been a number. There's been about 5, maybe 6 projects done here on the Willamette that are a little bit larger in scale. Go ahead. 2 of which have taken place on the South Fork McKenzie River. Go ahead. That's right. Thank you, Wes. I appreciate that. And I'm going to tell you a little bit why we're focusing on the South Fork. So go ahead. All right. So, you like that? I brought my own laser pointer. So, McKenzie River Subbasin, and the reason we're focused on the south, so the way we prioritize projects is, first of all, we take a look at, even though we try to move away from more of a single species type paradigm where we're worried about, we're designing projects around listed fish, really single species type restoration. We're really trying to move away from that. Unfortunately, the realities of funding it really dictates that we kind of stick with that paradigm. The great thing about salmonids, though, being kind of an umbrella species, is that you restore habitat for them. You're really benefiting a whole host of other species, and so the yellow and the green here represent spring Chinook habitat. That's right. Thanks, Wes. Go ahead. So this is all critical and historic spring Chinook habitat. Go ahead. We take out habitat that we can't work in either because of private lands or land use. We're looking at main stem McKenzie, huge recreation fishery. We can't really be putting large wood throughout all that and disrupting some of those million-dollar homes. Go ahead. We take out areas that are upstream of the dams because we haven't quite figured out passage at those high-head dams yet. What's great about the McKenzie, though, if you go back one slide again there, is McKenzie's really unique. We've got some really nice habitat in Horse Creek, Lost Creek, and some of these others in the upper McKenzie. So we don't really need to do a whole lot there, and they serve more as like reference type conditions. Go ahead. And that leaves, go ahead, a couple areas to focus on, including the South Fork McKenzie River and Deer Creek. Go ahead. So not the best image right here, but what we're trying to show here, once again, so this is a LiDAR image, laser image here, shot from and what you're showing here is McKenzie River here, South Fork coming right through here. If you're at all familiar with the McKenzie River, there's the unincorporated community of Blue River right there. After Heidi River Road comes up through here. And what you can kind of see through right here, the non-washed out part, is actually how many relic channels are throughout, or retained throughout this wide floodplain. The McKenzie River flows right through here and doesn't really access any of this available floodplain because of water management issues, because of residential, because of highway, whole 9 yards. Go ahead. Can't really see this one at all. But the other thing great about the South Fork is that we've got relatively few one road, one campground constraints on what we can actually do in terms of actually accessing and reconnecting this floodplain. Go ahead. Whew, that's a hard one too. So obviously with Cougar Dam going in 1964, a lot of impacts, really degraded habitat downstream of the dam. Go ahead. Go ahead, please. Thank you. Very few pools, very few gravels, very little large wood, very little connection to its floodplain because you've taken all those inundation flows away. You've taken away that downstream transport of gravel, of large wood. Go ahead. And so in about 2012, started up a joint project with the Forest Service to figure out more of like a 10-year plan on how to restore this creek, or this river, excuse me. Came up with a bunch of goals that really focused on trying to restore amount of processes possible, given the fact that the dam was still there, so that this would be basically a self-sustaining restoration project. Go ahead. And so what we came up with is a 4-phased approach to restore about 4 miles of the river. Ooh, thank you. 4 miles of the river from the confluence up to Cougar Dam. We implemented 2018, phase 1 in 2018, phase 2 in 2019, and we hope to do the next 2 in the next 3 to 4 years. Go ahead. Oh my goodness. Okay. So what these are supposed to do is colored photos that show actually how we design. I'm going to go ahead and flip through these. But essentially, this is talking about phase one. Actually, hold on, wait a second. So we got the South Fork right here. Go ahead, Maggie. These are, so using LiDAR, we're able to identify areas of the floodplain that either have artificial or natural deposits that are prohibiting floodplain connectivity. So these areas, these polygons here, are all areas where that 85,000 cubic yards is going to get cut. Go ahead. And these dark areas here are areas that are actually where you're going to take that material, fill into this incised channel here. What you can't see is this spot right here. There's his relic channel that the entire river was diverted into. Go ahead. Because you're putting water onto this floodplain surface that has evolved over the last 50 years without that water being on it, you need something on that surface so that it's not going to erode or channelize again. So we put large wood throughout. Go ahead. And then large wood throughout. Let's go ahead and skip that. Pretty quick little project summary. So we implemented this in 2018. Cost just under $2 million. By far the biggest project we've ever done. In fact, if you take all the projects that we've done over the last 25 years, it would be a fraction of that cost right there. And so it just really kind of gives you a little bit of scale about how big, or idea on the scale of this project. This is, all right. So this is phase two, the design map. I'm going to go ahead and skip through that. But the idea, actually, hold on one second there, Maggie. So the South Fork flows through here and there. And the idea was that we'd cut these areas here. They would open up a bunch of side channels through here. You take that material, you're bringing these incised channels back up, and you have connectivity from essentially that hill slope all the way over here. Go ahead. So this starts with diverting the river. Can't really see them very well, but these are those super sacks from the trivia. Fill those with local material. Go ahead. And this is a nice picture. It kind of shows how halfway through the process, diversion dam goes across the existing channel. Portion of the flow is still going down the old channel. Portion's getting diverted into the diversion channel. Go ahead. Until eventually all that goes down this diversion channel. Temporary diversion channel. Go ahead. Once that diversion, once the flow is, the old main stem is dewatered and the flow put into the diversion channel, we've worked with ODF&W and some volunteers to do fish salvage. We moved probably about 5,000 fish out of the dewatered channel. Go ahead. Series of both seines and, go ahead, electroshocking. We actually had some crews that came up from Cottage Grove, Al Kennedy, and the Coast Forks youth crew came up and assisted with that over the course of a week. Woo! That's right. All right. And so this is what happens in those cut zones. If you kind of remember that washed out map where we had those polygons, we go in there and we clear all vegetation with huge excavators, pile those up and save those for later use. Go ahead. And then start within those polygons. So what we've done, if we've identified a target elevation that we essentially cut these cut zones, shockingly enough, down to. It's a series of anywhere from 1 to 3 or 4 feet, and that material then gets, actually hold on a second before that material. So that's, actually go ahead and go. There you go. And so those cut zones, if you could see this a little bit better without the washed out here, essentially becomes the dry bottom of the new river. Go ahead. So that material from the cut zone then goes into the old dewatered channels. We're literally taking a D8 cat, taking this material out, and pushing that into the old channel. And that's kind of what you see right there. Go ahead. And dump truck loads. So each one of these dump trucks holds about 25,000 or 25 cubic yards. Phase 2 here, we moved about 32 cubic yards. And so in phase 1, we moved about 85,000 cubic yards. So do the math. I mean, it's essentially, once we get that creek or that river diverted, it's essentially a construction project where you're just moving material from point A to point B. Go ahead. Grade out that incised channel to that target elevation. Place large wood throughout. Keep going. Yeah. And then once you're done with the large wood, you do the dewatering and the rewatering in reverse. You close out that diversion channel. Go ahead. And put water back over your construction zone. And so go ahead and do this, and I want to go back and forth real quick. And so, yeah, that one right there. So keep an eye on that tree right there. So that's the water, that's the rewatered project area. And that's what it looked like dry. So same tree. So go back and forth a couple times. One more time there, Maggie. There you go. All right, next slide. So that's what that project looks like. And I was really excited about this afternoon. It's probably not going to show up really well. But what I tried to do with this picture is put the design on top of it. And I'll go ahead and, so the South Fork is coming in from the, right here in the upper right and curving around here. Oh, go back again, Maggie. So the pre-project flow was pretty much concentrated in that channel right there with a little bit coming right through here. And then so what this project did is cut that whole surface, cut portions of that surface, a little bit of that surface right there, and then what you get is, and then put large wood throughout, and what you get is a connected surface from there all the way across there. Go ahead. So what I tried to show here was was actually how that plays with the design map, but we'll skip that one since we can't see it. So some before and after pictures. Key in on these trees right here. So pre-project, you've got one channel dominated by cobble and boulders because everything's contained within that single channel. You've got these high velocity flows in spring and winter high flows that's flushing all these fines, these spawning gravels out of the system. So all you have left is these larger cobbles and these boulders. And so what this project then does is open up this surface right here and create a bunch of slow water habitat that Chinook, that lamprey, macroinvertebrates all need to thrive. Go ahead. This is a really interesting one as well. So kind of key in on this tree right here. What this does is shows a really good example of actually how this project changes not only the channel but also connects water to the floodplain. Can't really see it with the picture, but what you have here is a series of channels being created throughout that kind of that floodplain lobe right there. Another before and after. Go ahead and skip this one. This is an interesting one too because I really like this even though you can't really tell what's going on. It's a good example of how it takes a forested system to an aquatic system. One thing to kind of keep in mind with these forested systems too is historically these evolved flooding on a regular basis. With the dam going in, you've taken those peaks and those valleys of those high water flood events out, and the vegetative community has responded in kind. So really what you have is an area that would be, you'd expect to be more wetland dominated or mixed hardwood forest, is really showing more trends of an upland forest dominated by incense cedar and Doug fir. And so when you cut that, take those those cut zones out, what we expect to see is that vegetative community, because you've raised that water table to respond in kind, and we expect that vegetative community to change from Doug fir dominated forest to more of a wetland obligated and riparian obligated forest dominated by hardwoods and western red cedar. So phase 2, 60-acre project, diverted the entire 275 CFS flow into that channel that I talked about. We moved about 32,000 cubic yards. We had graded over half a mile of channel, placed about 1,200 pieces of wood, got it done in about 8 weeks. And the contractor that we used was BCI out of Portland. Coincidentally enough, they're the same folks that worked on the Nature Conservancy project at the confluence of the Coast Fork and the Mid Fork. Go ahead. Project cost just under $1 million to do. These are big ticket projects, but if you look at it broken out between at a cost per acre, so phase 1 costs about $13,000 per acre to do. This one costs about $16,500. Average together about 14,000 acres, $14,000 an acre. If you compare those to the cost of riparian restoration projects or some of those more traditional large wood projects, they compare really, really favorably. And we would argue that they get much more immediate response from the stream system and the biological community. Go ahead. And so what we've done in partnership with the Forest Service and OSU is embark on a 4-year monitoring project. So I actually think this talk will get a lot more interesting in about 2 or 3 years when we actually have some data to show how these systems are actually responding. We have some really anecdotal evidence of what we're seeing ourselves as project managers, which is really, really encouraging. We're seeing this wood that we place stay in the system. We're seeing huge numbers of both fry and adults using these project areas, but we don't have the data sets to actually prove that. But through this 4 to 5 year project with OSU, with the Forest Service, we believe we're going to get that data so we can actually start pushing these projects in more of a regional scale, and we really think we'll have a beneficial result on wider scale implementation of these projects. Okay. So what we're hoping to do with the what we're planning on doing with the monitoring projects is both a look at the geomorphic response and the biological community response of these projects. One thing that's been a huge struggle is the trying to actually talk in geomorphic terms of what these channels are actually doing in response to this restoration treatment. The tools that we've traditionally have in terms of stream habitat surveys, where you're going out and you're classifying pools, riffles, and you're classifying what the substrate is, how many pieces of wood in there, how deep these pools are, how many pools are just totally impractical in these project areas where you have essentially wall-to-wall water across 50 acres. There are not pools, or there are not defined channels. There is essentially just wetted surface across this wide area. And so instead of trying to fit a square peg into a round hole, trying to work with some of these researchers using new technology, using drones to define geomorphic changes, how complex these systems are in terms of the number of channels, the number of islands, how often they actually change course, what's the vegetation response doing, what's the wood doing. We want the wood, in these cases, to actually move around, but maybe not move out of the project area, because we don't want a bunch of wood moving into the main stem McKenzie River, obviously with boating concerns there. And there's some really interesting and developing techniques using remote sensing, not only drones, but also LiDAR, to track these changes over time. Go ahead. One thing we're also finding, though, is using that remote sensing, we have to have a ground truthing element to that. And so what we've done is establish 21 transects across the throughout the entire project area. Go ahead. These are super challenging surveys. Luckily, I don't have to do them. But essentially, and sometimes they take an entire day to do one transect. Essentially, what they're doing is walking a tape from valley toe slope to valley toe slope, taking measurements at each wetted area that they encounter. A couple of examples of some of the metrics that they use. Go ahead. And what they're finding, shoot. Well, this is a little tough, I guess. But let's take a guess. So what do you think is happening with the velocity here? Pre-post, it's probably going down, and that's what we're seeing. What's interesting, though, is actually the max depth and the mean depth. And I had a great trivia question for this, but we didn't need it because we didn't go to a tiebreaker. But the max depth, and both the max depths and the mean depth are staying relatively the same, which is a little bit counterintuitive, because you've taken water that was confined here and you spread it out over a wider surface. And so what do you think? I mean, you have relatively the same amount of water because it's coming out of the dam, and that's controlled and regulated. So you would expect, because you spread it out over a wider area, that both that mean and the max depth are probably going to go down. They're really staying the same, because what you've done is you've changed that velocity, you've slowed that water down, and so you're keeping that water on the landscape longer, which really has good implications for that water table and hyperetic exchange. And so not only are you holding that water there, it's infiltrating into sediment that's being retained in the system. It's infiltrating into surrounding riparian areas, being used by that vegetation. So we really, good example of how we expect that vegetation to change as well. We've changed essentially a riffle-dominated system into a pool-dominated system. Go ahead. And this is probably the most interesting data and really telling coming out of those transects is, so what this shows is the green is vegetation. That little spot right there is a tiny little side channel. And then this is the main stem channel. So we're looking at substrate. The darker the gray, the more coarse or bigger the substrate. And so there's your main stem channel, dominated by boulder and bedrock. Post-project, you've not only increased the width, the area of the wetted area, but you've also dramatically increased the diversity of the substrate, which is really, really critical for our native fish and macroinvertebrates. So this is kind of a fun image as well. Main stem South Fork, the dark blue is wetted area pre-project. Post-project, or the light blue is wetted area post-project at base flow. So summertime, you've taken flow that was all confined here, and dramatically increased that available amount of habitat. And so if you think about and you go back to those mean and those max depth graphs that we couldn't really see, you can really get a picture of how much we're actually increasing available habitat for native species here. It's quite dramatic. This is supposed to show an aerial image from last April, that high water event we had in March and April. This image corresponds really well to that modeled image. We just can't really see it because it's washed out. Go ahead. Each one of those transects, we're collecting both macroinvertebrate and eDNA samples, which I think are going to tell us a lot about how fast the biological community is actually responding to these projects and this huge disturbance. Go ahead. We're working with ODF&W to not only track adults, but also juveniles, Chinook salmon. So we're going to tag each year about 2,000 juvenile fish in this project, set up pit tag readers above and below the project, and tie those into pit tag readers at both Lieberg Dam and at Willamette Falls, and be able to get an idea of how long these fish are actually staying in this project area, so you get something about their life history, do some mark recapture studies, so actually to show how big they are. Data to date is showing that these fish are actually getting bigger, staying on the project area longer and actually emerging bigger. The idea that the bigger the fish, more likely they have better chance they have of actually surviving. Go ahead. Kind of the fun and really the leading monitoring that we've been leading with from this last year is the immediate response that we got from our spawners. So between ODF&W, the Army Corps, and the Forest Service, they've been doing spawning surveys on the South Fork about 30 years. What they found is somewhere between maybe a dozen or two reds annually in that lower mile and a quarter where we've implemented phase 1 and phase 2. Go ahead. What we saw this last year was 241 reds in this project. Yeah. So we'll take that with a little bit of a grain of salt because it was a very much a unique year last year. Very high percentage of about 5,000 fish that returned to the McKenzie were wild fish last year, and we had perfectly timed rain that brought fish into some of these tributaries instead of spawning in the main stem. But even with those kind of sideboards, it's really remarkable figure that was found last year with that spawning survey data to show that habitat is there 1 year or really immediately after the project. Okay. The other thing that I won't get into, but will be really cool in about 3 or 4 years, is there's a researcher from the Forest Service and OSU that are starting a food web study that's looking how that base of that food web is responding to these projects and really forming the basis for what we hope is a remarkable recovery for our native fish. So a couple take-home points. South Fork is the perfect place to do this kind of large-scale project because of really few limited constraints within the area. This stage 0 approach, even though I didn't get into a whole lot, has a huge initial disturbance area. You know, we're cutting acres and acres and acres of riparian forest, which is really counterintuitive to a lot of the messaging that watershed councils have had to the public over the last 10, 15 years. And so kind of describing the nuances and why that's a good thing in this case and maybe not in other cases, I think is a point that'll have to be developed and explored as we're doing more and more outreach and really talking about our monitoring results through this project. But even though we're having that huge initial disturbance, we're still seeing the biological community, at least with this initial anecdotal monitoring data, we're seeing the biological community respond. Go ahead. Can't even read those. So there's our project team. Had a really diverse funding assortment this year. We had corporate support from Intel. We had federal money. We had state money. And we even actually had county money for this project. And so if we're coming up with $1 million, we really got to kind of shake as many trees as we possibly can to come up with that funding. And that really, even though this is an 8-week project in terms of implementation, it's about an 8-month project in terms of sourcing that funding, doing that partner outreach, doing that public outreach, and securing that funding. So thank you for listening to me tonight. Sorry some of the photos didn't come through, and I'm happy to take any questions. I think you had your hand first. Yep. So another way that I think to think about that is disturbance. And so what are some of the primary mechanisms of disturbance? Volcanoes are one, floods are another, fire is another, landslides are another. We've developed all these systems in place to take away those disturbances, at least as many of those disturbances as we can. We can't really control volcanoes and earthquakes and landslides so much, but we've done a pretty good job of controlling floods. We've done really, well, in some ways we've done a good job of controlling fires, but in other ways we've done a horrible job of that. And so really this is a way of introducing disturbance back onto the landscape to try to mimic exactly what I think you're talking about. I like her. Yes, sir. So I think there's a couple things to respond to that. And so first of all, if we have kind of the event that you're talking about and Cougar Dam goes, this project right here is, I think, is going to be the the least of our concerns to some extent. But the second part of that is this project or this methodology is not a panacea. There are certain areas where it's completely the wrong or non-appropriate methodology. And one of the reasons that I don't think I did a very good job on describing is why we're working in the South Fork. Working in the South Fork because it has limited constraints. There are other areas like the McKenzie River in downtown Springfield where it'd be great in a vacuum to do this type of project and connect it to these huge sweeping floodplains next to north of the city of Springfield and the city of Eugene. You're not going to be able to do that because of homes and roads. But in the South Fork, I think what you're getting in other situations, I think you're actually getting a benefit because you're bringing that flow up, you're connecting it to this wider floodplain, valley to valley, or hillslope to hillslope, and I think you're actually going to get flood mitigation benefits, quite honestly, because you're spreading that water out instead of concentrating in a single channel and accelerating that flow. I would argue in the South Fork, in the spot where this project was implemented, that would actually help. In other places, like again using downtown Springfield, then I think you'd had some negative consequences. But once again, really with that type of geological flood, I don't think anybody really knows what those responses are going to be, and especially, how our infrastructure in terms of our flood control infrastructure is going to respond to that. Good question. Yes, right here in Lincoln.
So with the increased deforestation that's going on right now, like for instance, I live down Mosby Creek, and they put in some piers back there using boulders.
Mm-hmm. Yeah. So I'm not sure what the question is in there. More kind of a statement. Yeah. I mean, there's been a huge number of land management changes. Once again, I would go back kind of the statement to this methodology is not a panacea. Can't be applied everywhere. Actually, I think Mosby Creek, which I'm familiar with, is a really interesting system, undammed. It has huge incision problems. I think it's a poster child for what happens when you concentrate a flow into essentially a single channel there that doesn't have any or very little connection with its floodplain. And you see huge amounts of stream power in Mosby Creek. That whole channel that I'm familiar with huge sections have been flushed out to bedrock. And if you go and look at some of the tributary confluences, they're like 3 or 4 foot steps, bedrock steps from the main stem into those channels. And what that to me says is that's evidence of an unnatural system that is just flushing everything out. And so I think in certain cases, obviously there's constraints with the road and downstream private landowners, but honestly, I think elements of this design could work really well at Mosby Creek. Yeah. Yeah.
So with this type of restoration, is
great question. What we've seen and what we've been really nervous about and worked a lot with so actually let me repeat the question, thank you, is there a sedimentation problem? And yes, there is a sedimentation concern. We have not seen it come to be a huge problem quite yet. And that doesn't mean it won't happen. The concern is mostly, and where we've actually seen it be a problem, is around implementation. And so when we first take the water, when we first dewater the creek or the river, put it into a diversion channel or whatever that new path is, especially this last year where we actually constructed that channel, you couldn't see it because it was really faded there. But we had about a day and a half where we turned about a quarter-mile section or about a half-mile section of the McKenzie River on a Sunday afternoon, halfway brown. And so that was an issue. And so what we did is we went back and kind of redesigned that diversion channel to harden it up a little bit. Lesson learned, and we think we can prevent that into the future. What we haven't seen so much is the natural sedimentation with that first natural turbidity episodes with those first kind of winter or spring flushing flows. Once again, I think really because you're addressing that velocity, that stream power issue, spreading that flow out, where a good example is last spring with the March high water that we had that caused so much flooding here in the Coast Fork. What the Corps actually did is use the South Fork as kind of the holdback, and so held that water back there, brought it to full pool, and then about a week after that high water event, started releasing that water into the South Fork. We saw really kind of some of the highest flows we've seen in the South Fork for 5-10 years, about 5,000 CFS. We're really excited to go out there and see what that project looked like at 5,000 CFS, and we went out there and it was actually completely underwhelming. The water was calm, the wood was barely moving, and it was all clear, just because you've connected surfaces and you've addressed that stream power and velocity. That's not to say it won't happen. The other reason why I think the South Fork is really a kind of a perfect place to implement and test this scale of restoration using this methodology is because you have a controlled system. It's a little bit more unknown, and there's a whole lot more variables in an undammed system of that magnitude. And so maybe instead of 10,000 or 5,000 CFS, last spring we would have had 15 or something like that, and I can't say what would happen at that. Sorry. That's a great question. So the question is, so we're raising the, so we're taking vegetation out, we're taking that shade away, which we've been telling landowners for years and years is critically important, you have to take care of it, and we have set up all kinds of regulations about it. We're increasing surface area, so we're getting more thermal impact, right? And, but what we're actually seeing in certain cases is we're actually seeing that water cooling in certain cases, not in all. So in some cases where we're seeing it warm up, I think we're getting exactly the scenario that you're describing. But in other areas, we're actually seeing it cooling, and I think what's going on there is that you're actually getting more of that hypereic exchange, where that water is infiltrating into that substrate, stored underwater, filtering itself, staying cool, and then emerging back out downstream. And so what we're seeing, so I didn't mention it, but each one of those transects, we've established, well, there's 21 transects throughout the whole project area. We're only actively monitoring about 5, because what we just discovered is monitoring 21 transects is a heck of a lot of time and really expensive. But the ones that we are monitoring, we've established groundwater wells there. And those temperatures, those groundwater wells are showing, yes, we're not only raising that groundwater, but we're actually cooling it. And so I think what we're doing there is we're increasing. We don't have a good mechanism for saying what's happening across the board with temperature, but based on what we've seen with those temperature monitoring with the transect is we're getting essentially a patchiness where some areas are warming up, but other areas are cooling. And so what we really kind of, the hypothesis is that patchiness is going to end up being, I hesitate to say more natural, but a net benefit essentially, because well, yes, you are warming certain areas, you're creating refugia areas that the fish will seek out and utilize and benefit from going forward. The other thing that I think will change dramatically over time is the vegetation response. And so these open channels that are open to solar radiation are going to get vegetated. You're going to get we're already seeing a really impressive response from native willows, cottonwoods, that 5-10 years from now are going to be providing that shade that we've been telling folks for 5-10 years, 20 years that is really critical. Yeah. Oh, I thought I had. All right. I'm sorry. Yeah. So great question. The question is about fine sediment. Sure.
And that is, can you assess ahead of time the quality of the soils in the area and their potential to respond to the flooding?
Sure. So the question about fine sediment, and can we do some analysis ahead of time to kind of get an idea on response. And so to answer the second question first, yes, we can, but not necessarily for those reasons. What we discovered through phase 1 is a lot of times we didn't know, so we're disturbing like 15, 16 acres in phase 1, and we're digging down sometimes as deep as like 5 or 6 feet or maybe even more. We don't know what those soils are. And we've got a good idea if we go up and kick the dirt or look at the vegetation of what to expect, whether those are going to be fines or cobbles or gravels. And so one thing that we did based on lessons learned from phase 1 into phase 2 is we went and dug some test pits. We brought a small excavator in and dug a series of 20 test pits that kind of helped us inform and say, yeah, we want to work in this area. Maybe we don't want to work in that area. And so that's one thing we have kind of adapted to. That answer your question? Okay, perfect. The second part, and I'm glad you asked that question, is we've been, similar to talking about shade, we've been talking about erosion as kind of the boogeyman for 10, 20, 30, 40 years. And when the reality is, it's a natural process, especially these systems here, they need sediment. They're sediment starved because of the flood control system that we have in place that allows us to live in Eugene and Springfield and throughout 75% or whatever of the Willamette Valley. And yeah. And so one source of that sediment is that lateral migration of these channels to erode and add sediment to these systems. And when we focus a lot on gravels, because salmon are the sexy species and they need that for spawning. But one thing that we don't really focus on is all these other critters like Pacific lamprey that need sand and these fine sediments for Pacific lamprey are amazing. Anadromous fish, but they spent that live for like 8 or 9 years, but they spent 7 years or more buried in the mud in fresh water, and if they don't have those fines, they can't complete their life cycle. And so they filter feed in these deep beds of fine material for years and years and years before going out to the ocean, attaching to whatever mammal or whatever salmon and coming back. And so I think this is a way to at least get at some of those more natural processes and that we've lost just through our land management practices. And so erosion in certain cases, yes, is a bad thing. In other cases, it's actually a really good thing and something that we want to encourage where it's appropriate. And so I think that gets back to areas that we have constraints, that maybe we don't want to implement this type of projects, but areas where we don't have those constraints, that let's rethink how we look at those how we look at that landscape, and can we implement these essentially large-scale, whole valley landscape projects that are getting away from that single species paradigm to where we're looking at restoring as many processes as we can and restoring as many ecological functions as we can, and benefiting as many species as we can, water quality, the whole 9 yards. And I think erosion is a good example of that. So thank you guys so much.